Okay, so today we're going to talk about finding the derivatives of trig functions. And of course, just like the previous sections, we're going to learn these shortcuts. Okay, and so once again, just to point this out, the shortcuts were, of course, discovered through the definition of a derivative. So, when I show you these shortcuts or when the derivative of a trig function is something else, if you're wondering how would I show it, well, if you were to basically grab each trig function and if you were to apply the definition of a derivative, you'd see that you'd get exactly what I'm going to give you. So today, I'm not going to derive the derivatives because we've spent plenty of time deriving derivatives through the definition. I'm just going to give you kind of what the derivative of each trig function is, and then we're going to put these to use. Okay, so before we do that, there's a couple of limits that I want to bring to your attention because we will be using it from time to time. So we know from previous chapters or previous sections that the following two statements are true. So limit as theta approaches 0 of sine of theta over theta. And if you remember, we've seen this before. This equals to 1. And then the second limit is limit as theta goes to 0 of cosine of theta minus 1 all over theta. That was 0. So if we encounter these limits, which we will not only in this section, potentially in sections to come, just remember that this is kind of like a recurring theme, and we'll come back to this over and over. Okay, so with that said, let's talk about derivatives of trig functions. And let's start off with sine and cosine, and then we'll see what happens with these. So the derivatives of trig functions are defined as follows. And my recommendation to you is these shortcuts, you'd probably want to just memorize these. But if you forget and you don't know what the derivative of, let's say, sine is, you could always use the definition to derive it and find it, okay? But, if I ask you to just tell me, for example, the derivative of sine of x, you can just give me its derivative right away. So the derivative with respect to x of sine of x is, in fact, cosine of x. And then we would say that the derivative with respect to x of cosine of x is negative sine of x. So what we start noticing is the derivative of sine is cosine, and then the derivative of cosine is negative sine. And I hope you understand, or it makes sense to you, why the derivative of cosine is negative sine. Because if you remember, the graph of cosine kind of starts at a maximum and works its way down, which notice its slopes of its tangents are kind of negative to begin with. That's why this negative comes about. But once again, if you were to use the limit as h approaches 0 of cosine of x plus h minus cosine of x all over h, if you were to use that definition, you get negative sine of x. And of course, you'd probably end up using these properties in the process to help you figure these out. Okay, so let's move on. We can also find the derivative with respect to x of tangent of x, which that becomes secant squared x. And then we have the derivative with respect to x of cosecant of x, which that becomes negative cosecant x cotangent x. And we have two more derivatives. The derivative with respect to x of secant of x is equal to secant of x tangent of x. And finally, we have the derivative with respect to x of cotangent of x, which gives us negative cotangent, negative cosecant squared x. Okay, so basically these are the derivatives of our trig function. So I would highly recommend that you memorize these because you can go ahead and use these whenever you're not asked to use the definition of the derivative to find these. So these are kind of like your shortcuts to the derivatives of your trig functions. Okay. Now, one comment I want to make here is these derivatives are only valid when theta is in, or our angle, or x is measured in radians. Okay, so these are true only when x is measured in radians. Okay, so with that said, just keep in mind that um, in this class, we always work in radians. Okay, so we never work in degrees. So keep that in mind. So your calculators, you should always make sure that you're in radians, because we're not going to ever work with degrees when it comes to trig functions. We're always going to work in radians. And of course, radian measure is preferred over degree measures because it has a lot of advantages as opposed to degree measure. Okay, so let's just do a bunch of examples, and then that'll pretty much wrap up this section. Okay, so this section is not a long section. We're just kind of putting our whole derivatives to use, okay, of as far as these trig functions go. So the first example is going to be differentiate f of x equals to x sine of x. So if you look at this, when you're trying to find the derivative of this, notice how this is a product of two functions, which means to find the derivative of this guy, I have to use the product rule, because I'm taking function x and I'm multiplying it to the function that's sine of x. So using the product rule, the derivative will be, and remember, talk yourself through these derivatives. The derivative of the first, which is 1, times the second, plus the derivative of the second, which the derivative of sine is what? Cosine of x times the first. So just to simplify this a little bit, I get sine of x plus x cosine of x. Okay, so notice how, of course, to differentiate this, I had to use the product rule, because the product rule was holding all of this together. Okay, now moving on to example 2. Differentiate f of x, or f of u, let's call it. Let's just change up our variable. E to the u times cosine of u plus cu. Okay, so now if you look at this, when I find a derivative, notice how, well, e is a number. We already know that that's 2.72 or whatever, 2.71, so on. But this function is telling us what? The variable here is u. So e, of course, is a constant, but what am I going to treat c as? Well, c is not my variable, so c is a constant. Okay, so once again, to find the derivative of this, notice how I'm taking e to the power of u and I'm multiplying it to cosine of u plus cu. So to find this derivative again, I have to use the product rule. So f prime of u will be the derivative of the first, which, what was the nice result we got from last section? The derivative of e to the u will be e to the u again. So the derivative of the first times the second plus the derivative of the second, which derivative of cosine is negative sine u, plus the derivative of cu will just be c times e to the u, the first. And so once again, remember how I told you guys that, look, once you find a derivative, you could move on. If you're to simplify this, I wouldn't distribute the e to the u. Instead, I would factor out the e to the u. That would make things even better. Okay, so this is basically our derivative of f of u. Okay, so let's move on to example 3. So here, this example, we're going to basically prove, so we're going to say prove that the derivative with respect to x of cosecant of x equals to negative cosecant x cotangent x. So basically, we're being told to prove that the derivative of cosecant is negative cosecant cotangent, okay? So what they're saying is, so notice how this question isn't specifically saying you have to use the definition of a derivative. It's just saying, look, you can't use the fact that the derivative of cosecant is negative cosecant cotangent. You need to show this. But we could also use the fact that, for example, the derivative of sine is cosine, or the derivative of cosine is negative sine, and so on. So how would I prove this? Well, we first start off with cosecant of x. And what I know is we could rewrite cosecant of x. So let's call this f of x is equal to cosecant of x, which cosecant of x is the same thing as what? 1 over sine of x. So if I'm finding the derivative with respect to x of cosecant of x, isn't that saying the same thing as finding the derivative with respect to x of 1 over sine of x? And see, this I could find a derivative of. Now, if you look at this, what have I written this as? I've written this as a quotient. Okay, so as a quotient, how would I find a derivative of this? I would have to use the quotient rule. So what would that be? The quotient rule says, remember we kind of talk ourselves through this, is what the derivative of the top. So I'm going to put 1 prime. So I'm not saying 1 to the power of 1. I haven't found a derivative yet, but I'm saying I have to find the derivative of the top times the bottom minus the derivative of the bottom. This is the prime, so I haven't literally found the derivative of the bottom just yet, minus the derivative of the bottom times the top all over the bottom squared. Okay, so now let's complete this. So 1 prime, the derivative of any constant is always 0 times sine of x minus the derivative of sine, which would be cosine of x times 1 all over sine squared x. Okay, so let's simplify. 0 times sine, that goes away. So what do I have left here? Negative cosine of x over sine squared x. So you might be looking at this and say, okay, I found the derivative of 1 over sine, which is what cosecant is, but it's not giving me negative cosecant cotangent. But if you're good with trig, you could manipulate this, can't you? Can't we rewrite this as sine squared is the same thing as sine times sine? So can't I rewrite this as minus 1 over sine x times cosine of x over sine x, which notice how all I did is I just kind of separated these guys and I gave the cosine and I took the minus away from the cosine. So negative 1 over sine x is what? That's negative cosecant x. And cosine over sine is cotangent x. So there you have it. What did we just show? We showed that the derivative of cosecant x is the same thing as negative cosecant x, cotangent x. So this is another way. As long as you remember the derivatives of sine and cosine, you could derive all the other derivatives. But see, just to save yourself some time, you're better off just memorizing these derivatives so you don't have to worry about deriving them. But if you don't remember them, don't worry. It's not that you won't be able to figure these out. As long as you remember the derivatives of sine and cosine, you could find the other ones without a problem. Okay, so this takes us to the last example. Okay, and example 4, this is a limit problem which will put to use what we talked about earlier on in this section. This says find the limit as t approaches 0 of sine squared 3t over t squared. Okay, now, if you remember, one comment I want to make before we simplify this, if you remember, we have a property, which was property 1, if you remember, we said limit as theta approaches 0 of sine of theta over theta, that's going to be 1. And by the way, just to point something else out as well, do you think it would be different if I did this, if I rewrote this as limit as theta goes to 0 of theta over sine theta? Do you think this would be a different result? And if you answered no, you're correct, because what is this? Basically, this is the reciprocal of that. So look, as theta goes to 0, if this approaches 1, what's the reciprocal of 1? It's still going to be 1. Okay, now one other comment I want to make before we go ahead and solve this problem, because I haven't solved it yet. I'm just kind of talking about this property here. See, what does this limit say? This says as long as this theta, that's the angle that's attached to sine, as long as this and what's in my denominator, if these variables are both the same, so then sine of theta over theta as theta goes to 0 will be 1. So what I'm trying to tell you is, for example, if I have limit as x approaches 0, for example, of sine of 10x divided by 10x. See what changed from here to here? instead of 10x, we have theta. But what is this saying? As long as this angle and this denominator are both the same, and if you send my variable to 0, this will always be 1. So in other words, since this is sine of 10x divided by 10x, and since this 10x is the same thing as that 10x, and as x goes to 0, this will also equal to 1, because the rate in which this 10x and this 10x approaches 0 will be the same. Okay, so so just to make sure you understand, if I were to do this, if I say sine of 2x over 5x, this equals to 1, would that be correct? And the answer to that is no. How come? Because this is 2x, this is 5x. They're not the same. So I can't say that that's 1. As long as this angle and what's in the denominator are the same, then I could say the limit as that theta goes to 0 will be 1. So this is 1, but this one isn't, because 2x and 5x clearly are not the same. So with that said, let's come back to this example. And what we want to do is we want to find this limit. Now, if you look at this, I definitely want to use this property with that. But what's the problem here? Over here I have sine, but here I have sine squared, and I have t squared. So what we notice is I want to try to get this to look as much as like that as I can. So what I could do is I could factor it, because if I have a sine squared here, I could rewrite this as what? The limit as t approaches 0 of sine of 3t over blank and sine of 3t over blank. Okay, so and then I could also separate the t squared, because I have two of them. I can get it to look like this. Okay, so far what you notice is I'm getting this to look like that. But what's the problem still? If you look at this, could I say this is 1 and this is 1? So think about it for a minute. Could I say this is 1? And you should say no, because the reason why this isn't 1 is because, remember what I said, t is approaching 0, which that's good. But in order for this to approach 1, since this is 3t, this also has to be a 3t. So if I could somehow manipulate this and get this to have a 3 and this to have a 3, then we could actually put this whole property to use. So the good news is we could do that, because look, how could I get this t to have a 3 down here? Well, what if I multiply the denominator by 3? But remember, to keep things consistent, what does that mean? If I multiply the denominator of this guy by 3, then I also have to multiply the numerator by 3, because remember, my goal is to multiply by 1. I'm just manipulating this, so it helps me kind of get what I want. But at the end of the day, I'm really just multiplying by 1, which isn't changing what's happening here. So then let me ask you this. How could I get this to have a 3 in the bottom? Because remember, this 3 goes to that t. So this t also needs a 3 to match up with that 3, which, if you've guessed, we do the same thing. We multiply the bottom by 3 and then the top by 3. So if I do that, look at what I've just created. This is limit as t approaches 0. And this 3 and this 3, I actually don't want to put up there. So can't I just take this 3 times 3, which is 9, and isn't there a property of limits where I could move that out front? So here, let me show you what I'm talking about. It'll be sine of 3t over 3t times sine of 3t over 3t. Now, if you look, one thing I want to point out is this is still the same thing as what we started off with, because look, this 3 and this 3 together give me the 9, and that 9 basically cancels everything out, which takes me back to that. But the good news is this. Since this 3t and this 3t match up, and this 3t and this 3t match up, what do I know? The limit as t goes to 0, this should go to 1. This should go to 1, which that means, what do we get? We get 9 times 1 times 1, which the answer is 9. Okay, so I hope this manipulation makes sense to you, because that's kind of, we're using this property to help us out to get to our solution here. So just keep that in mind. You know, if I gave you, for example, now pretty much our notes are done, but I just want to make one last comment before we wrap up here, is see, what if I had something like this, limit as t goes to 0 of I don't know, t over sine of 2t times sine of 7t over t. See, what would you want? You'd want this t to be a what? A 2t, just so it matches up with this. So how would I do that? I would multiply top and bottom by 2. And then for this guy, I would need to multiply this guy by 7 because I want this 7t to be the same as that 7t. So just remember, whatever sine of this is, I want whatever's in the numerator or denominator to be the same as whatever the sine of this angle is. So I'd multiply top and bottom by 7. So what you'd notice is, see, this 2 should go with that t. This 2, we can say, okay, I can't get rid of it, but I can grab this 2 and this 7 and just put it out front and say, look, this becomes limit as t goes to 0 of 7/2 times 2t over sine of 2t, and then sine of 7t over 7t, which then you'd say, well, as t goes to 0, this goes to 1, this goes to 1, so we get 7/2 times 1 times 1, which the answer ends up being 7/2. So for these problems, it's all about how you manipulate them, okay? So that basically wraps up this section. Remember, just to recap, we learned how to find the derivatives of trig functions by using the shortcuts. And we worked with evaluating some limits where we had to put to use the whole idea of limit as theta goes to 0 of sine theta over theta. And of course, we also had a limit that related to cosines, which you may also put that to use. Okay, so that takes care of this section.